This is lecture 9, mostly review, but we will do an example, and also I want to introduce experiment number 4. So a review here, we've been looking at program flow control. Program flow control are essentially branches and jumps and subroutines, which subroutines are calls and returns. So a call and return and is actually, they're both pseudo instructions. A call is a combination of these two instructions, and a return is a jump and link register. So we talked about the reasons for a jump and link register before, but in general, program flow control is just a matter of jumping somewhere else in your program rather than executing the next instruction. Big difference between the JAL and JALR instructions, so that's jump and link register. And it's a difference you need to understand, particularly later on. You got to implement this stuff. So jump and link, they both do this operation right here, which is essentially saving the address of the instruction following these two instructions. It's saving it into a register. Essentially, that's going to be a return value. So you can actually use either of these instructions for a subroutine call. The difference in these instructions is in how what it sticks into the PC when it returns. And the notion here is in the jump and link register, here's the register. That register is understood to be the return address. Okay, so these can just be immediate values depending on how you use them. But remember, the jump and link, both these instructions can be used to call subroutines. Only the jump and link register can be used to return from it because it has a register value sitting there. And if you remember, when we executed subroutines, what we did was we stuck the return address somewhere, which is the address of the instruction following the call. We put it somewhere, which is in the return address register, and we reloaded that back into the PC. So essentially, that's what the intuitive notion here is of a subroutine is. I'm not going to execute the next instruction. I'm going to jump somewhere else, and then I'm going to jump back and then execute the next instruction. So I need to store the value of that next instruction, which is going to be the return address. So typically we push the return address onto the stack, and X1 is typically we use as a return address. X1 is, you can also call it RA, and this is one of the reasons why we don't use X1 and X2. Stack is just the abstract data type, which means we define it by the way it operates, not so much the low-level details. So what we can do is push and pop, which means save and restore stuff from this. And the top of the stack is the latest thing we put on the stack, and the stack pointer points at the top of the stack. So these objects, this abstract data type, is just, we implement it in memory, but it is a classic last in, first out data type, so that therein lies the difference between, we'll say, normal memory and an abstract data type. It has to do with the addressing of data. There are no push and pop instructions in the RISC-V architecture. What we use is load and store instructions, and essentially a push is a store word, and a pop is a load word, as you can see it written down here. And essentially you push something onto the stack, we're saving it, popping it off, we're essentially restoring it. So as you remember, all load and store operations involve registers. So when I'm storing something, it's from a register into memory. When I'm loading something, it's from memory into a register. They're all register based. So the couple different ways to do pushes and pops. These are the pushes and pops as I know them. Best way is to do the green, what's in green here. So the idea is adjust the stack pointer. Essentially you're adjusting it backwards 4, that means 4 bytes, and you're pushing the value on the stack. So it's using the stack pointer as a base register. It has an offset there, and this is the value that's being stored. And okay, on the end, this is the address SP. It's pointing at the last thing I put on the data on the stack. I'm taking that data off the stack, putting it X8, and then I'm advancing the stack pointer. So by convention, stacks grow in the negative direction. So this was one of our subroutines. This is actually a subroutine calling another subroutine, and because it's a subroutine calling another subroutine, I have to store the return address of the first subroutine onto the stack, and that's what I'm doing right here. I'm storing that on the stack before I leave. I have to store it there before I make the call. Before I leave this thing, I am restoring it. So this is your push, and this is your pop down here. This notion of bulletproofing subroutines, essentially what I want to do is protect all the registers, or essentially save all the registers that the subroutine uses on the stack, so that way the calling program doesn't have to worry about having its data stepped on. And then when I exit the subroutine, I pop everything off the stack, well, before I exit. So if it's a nested subroutine call, I also for sure have to make sure I save the return value on the stack as well. And so we made this program a while ago, essentially just summed up 32 values in memory and then took the average of it. And so this was our base code here. It looks pretty short and doable. The problem with this code is that it may step on code from the calling subroutine. So what we do here is take all these registers that are used in this subroutine and push them on the stack before I do the work and pop them off when I'm done. And this is what it's going to look like in the end. It's the same body of the loop right here, but here's saving in the context, and here is restoring the context, and that shouldn't say init, but whatever. So the idea here is I add more instructions to it. It's going to increase the length of the program, but it's going to make the program much more usable. So in the end, when you're encoding subroutines, you typically, they should follow the same structure. A header describing everything about the subroutine, like a description, certainly what you're sending the subroutine, what the subroutine is sending back, and by all means the tweaked registers also. Whatever registers that you're going to use in there, you should let the programmer know. So if you do all this stuff, it's going to make your code very usable for other programmers. So typically every subroutine, you got to initialize stuff. Typically it's saving context for one, and that means saving the registers. But typically we have to initialize some values also. So that's part of the initialization sequence. Body of the subroutine, yes. The return preparation, essentially pop everything off the stack, and you're ready to go. You're ready to return. So that's it. So this is experiment 4, and this one is kind of an interesting experiment. Essentially, it's to generate 2 modules in the RISC architecture, and after this we'll be doing the control units, and we're actually experiment 5. You're going to have to implement a working computer. So the data, typically what we're interested in is the immediate generator here. So there's a notion of immediate data used by the instructions, and so here's some examples there. This is an add immediate instruction. There's the immediate data. These are also immediate instructions that use immediate. There's the immediate data, and there's the immediate data for these branch type instructions. So this is very straightforward experiment. Like I say, after you spend a couple hours toiling with it, trying to figure it out, it shouldn't be that big of a deal. I'm hoping I described it much better, and it actually has some description in the text too, as well as the experiment write-up. So by all means, take a look at those. So anyway, this is the full architecture. These are the 2 modules we're interested in. We've already implemented that. We've worked with that. This is going to be given to you. This was experiment 3, and we're ready to move on to this thing here. So experiment 4, it's another simulate only experiment. I'm going to provide a test bench for you, and the good news is that once you're done with this, you'll have 2 working modules. You don't have to worry about these in any part of your other experiments. So the only problem is I did put one small little kludge in here, but it a little bit confusing, but it helps you read the output of your experiment. So this is the experiment. This is the experiment setup that we're going to do. So this is, get this drawn right here. This was from the other experiments. You already did this. This is given. These are the two new modules that you're going to implement in this one. So it's not exactly the way you're going to do it, because you have to do this little kludgy fix in here, and that's going to make it easier to read. But these are the two modules that we're going to be implementing in this experiment, and so we can look at those in a little bit greater detail here. Oh, there's the picture again. Oh, there's the whole picture. Not a big deal. So it's very much the same thing. It's just missing that +4 there. So the immediate generation module is, this is it here. It's going to take the immediate bits as part of the instructions, and there can be up to 25 of them. It's going to take those immediate values, and it's going to change them into 32-bit values. Okay, so these immediate values are relative addresses. It's going to make them into 32-bit relative addresses. It's still going to be 32. It's still going to be a relative address. And so here are these are the 5 instruction formats. So each, like I said, these are the 5 instruction formats. Each of them has an immediate field in it. So for example, there's the immediate field. These are the immediate fields. They're actually broken up in these, and these are the immediate fields in those. So what you're going to do, so here's an I-type instruction. You're going to take this immediate field, which is 12 bits long, and format it to look just like that one. You're going to make it into 32 bits, and the way you're going to do it is, you can see this I of 31, maybe, hopefully. Essentially, you're going to take those 11 bits or 12 bits and sign extend it. So this is like 20 bits of sign extension. So I'm going to do that for each of them. For example, this is the J-type instruction. So these are the immediate bits, and I'm going to make those immediate bits look like this set of 32 bits. Okay, so I'm going to do that for all of them, and that's essentially the module. It's going to take these input bits, which is 25 bits, kick out these 32-bit values according to this instruction, this format right here. Okay, so the branch address generator is the lower module on this thing. Essentially, it's going to take a bunch of data here and generate a absolute address, because essentially these instructions right here are going to the program, the mux in front of the program counter, which takes absolute addresses. So I'm taking relative addresses from the other part of the circuit, and I'm generating absolute addresses. Okay, so that's for these 3 things. These instructions are a little bit special. Essentially, I am just using those in another part of the circuit, but this part is for the branch address generator. So once again, these 3 here, all these values are going to be used to determine these absolute addresses. And if you look in the manual, you can see the documentation is going to take some combination of all these values and kick out these 3 values, which, I don't know what they are. It's in the cheat sheets or in the assembler manual. So take a look at that. Once again, these 2 instructions are just 2 other important type of instructions that I'm going to verify I did right. This is a test program. You're going to assemble this thing and drop the machine code into your memory object. Then you're going to step through the simulator and look at it. Okay, so when it's executing this instruction, you should be able to see an 8 on the JAL output of the branch condition generator. Okay, so when you're executing this instruction, you should see 4 on the JAL output of that branch condition generator. Okay, same with this one, BEQ, I should see a 4 on the branch output. Other than that, there's 2 other instructions here. I should, when I execute these instructions, I should see a 12 on the S immediate value, and on the U immediate value, I should see this on the output. Okay, so once again, you're not going to see, it's not going to jump. It's not going to take these jumps or anything like that because it's not hooked up properly. What you're going to do is look for these values on the simulator, and if you see those values, you know you've done it right. Okay, so that's it. I'm going to go scan back to this thing. So once again, I am going to execute those 3 JAL, JALR, and branch instructions, and I'm going to look at these values and see if they're there. But I'm also going to look at the S-type value and the U-type value for the other 2 instructions in that little program. So I'm interested in these 2 things for these 2 instructions right here. So these have to do with the branch condition generator. These have to do with the output of the circuit itself.